In this lecture, we're going to discuss optimistic concurrency control, which tries to increase the level of concurrency or transactions per second compared to pessimistic concurrency control. And this is important because it improves the revenue, it improves the operations per second, and it lowers latency. Okay? And these are important even in non-transaction systems. So systems like Dropbox, Google Apps, Wikipedia, key value stores, Amazon's Dynamo, all of these, even though they don't support transactions necessarily, they prefer optimistic concurrency control approaches because it reduces latency and increases concurrency, meaning it improves operations per second. Optimistic concurrency control in general is preferable over pessimistic concurrency control when conflicts are expected to be rare. But when conflicts do occur, you need to make sure that they are caught and resolved if necessary. So the most basic approach to optimistic concurrency control is to just allow transactions. We're going to be discussing the transaction version of optimistic concurrency control. You just allow transactions and clients to read and write objects at will. When the transaction tries to commit, you check for serial equivalence. If it's violated, then you abort the transaction and roll back any updates that it made. Now, an abort by a transaction may result in other transactions that read dirty data from this transaction also being aborted because that data was never ever reflected based on atomicity. Those are the transactions that read the dirty data by an aborted transaction also need to abort. But those transactions may have written data which may have been read by other transactions, and those transactions now transitively also need to be aborted. As a result, transaction aborts are a little bit tricky because one transaction abort might lead to a series of other cascading aborts of other transactions as well. So a second approach that tries to improve on this is known as timestamp ordering. This is used by several databases. Each transaction is assigned an ID. It's called the transaction ID. The transaction ID determines that transaction's position in the serialization order. So you want to make sure that you have a serial equivalence order that obeys the transaction ID ordering. When a transaction T executes an operation, you need to make sure that two conditions are true. T's write to an object O is allowed only if transactions that have previously read or written that object O had lower IDs than T. Okay, that's the first condition that needs to be satisfied. Second condition is that if T is trying to read an object O, that is allowed only if O was last written by a transaction with a lower ID than T. Okay, so if these two conditions are satisfied, then you can ensure that the transactions, even though they interleave their operations, follow the serialization order and that the resulting interleaving is serially equivalent and the ordering is the serialization order. Typically, timestamp ordering is implemented by maintaining read and write timestamps for the object. And whenever any of these two rules is violated for a transaction's operation, then the transaction is aborted. So this works for serial equivalence, but still you're still causing transactions to abort over here, right? You don't have cascading aborts anymore here necessarily because the transaction only aborts and that's it. Or at least the cascading aborts are minimized over here because the transaction can still abort and other transactions can be caused to abort because of it. But the aborts are minimized compared to the previous approach that we discussed on the previous slide. But essentially what I'm saying here is that you still have aborts and you might still want to do better than this. So a third approach is known as multi-version concurrency control. This is used in several systems, including some key value store systems like React. Here, for each object, you maintain a per transaction version of the object, right? And so each transaction maintains its own tentative version of that object. You also have a committed version, which is maintained on the server side or on the database side. Each tentative version has a timestamp of its own, and the committed version also has a timestamp. Some variants, some systems implement both a read and a write timestamp for the tentative version. Whenever a transaction wants to do a read or a write, you need to find the correct tentative version to read or write from. And this correctness, which is the correct version to choose from, is based on the transaction ID. So you want to make sure that you read only from transactions that were immediately previous writers. Okay, so you choose your point in the transaction among the versions of that object, and you choose the right version to read or write from. Okay. So this is only the sort of high-level overview of multi-version concurrency control. We are not discussing all its gory details, over here. Now, eventual consistency that you've seen in key value stores is in fact a form of optimistic concurrency control. In Cassandra key value store you've seen, in the DynamoDB key value store, and also in the React key value store. But these systems are not transaction systems, so the optimistic approach looks different. In fact, it looks slightly simpler in some ways. So in Cassandra and DynamoDB, there is only one version of each data item, each key value pair. That's what we would call an object. And you have a last write wins or last writer wins policy, which is LWW. Essentially, the timestamp, typically based on physical time, is used to determine whether to overwrite the older value. If the new writes timestamp is higher than the current object's timestamp, you overwrite. Otherwise, you do nothing and you ignore that write. So this ensures eventual consistency, which means that eventually when writes stop, all the replicas will reflect the same value, which is the latest timestamp write. But you could have situations where a slightly older write with a fresher timestamp, because of unsynchronized clocks in a distributed system, a slightly older write with a fresher timestamp might in fact win. And so the last writer wins really is based on the notion of physical time and assumes some notion of time synchronization across clients. A different approach used in the React key value store uses vector clocks, and you should be familiar with vector clocks because you've studied them in the first half of the course when we discussed Lampo timestamps and then vector clocks. This notion implements causal ordering, and these vector clocks are used to detect whether a new write is strictly newer than the current value, if the vector clock value is strictly greater than, or if it's not compatible, then the new write might conflict with the old existing value. If there is a conflict, then you create a sibling value, meaning you maintain for that key two values, saying that these are two possible values for this key. These are sibling values. These need to be resolved at some point of time. They could be resolved by the user. You could bubble them up to the client or the user, which then picks one value and then does a write using that value and overwrites the existing values with a newer timestamp. Or it could be resolved automatically by the application. So in any case, these are not resolved by the React system itself. They are pushed out to the client either by the user or by the application itself. Now, React uses vector clocks, and the vector clocks might get very large because the number of entries in the vector clock is potentially the same as the number of clients. And so to prevent a vector clock from getting too many entries, you use size-based pruning. You typically prune the number of entries, the maximum number of entries that can be there in a vector clock. Also, vector clocks might get very old. Some entries might have very old items, vector clock values in them. And so to prevent that from happening, you prune out or you remove entries that had very old timestamps in them. So to wrap up our discussion of concurrency control, we first discussed RPCs and RMIs, remote procedure calls and remote method invocations, which are important building blocks in understanding what transactions are. Transactions are one of the most important concepts in database systems that have been used for many decades. For transactions, you need to maintain asset properties, and to maintain asset properties, serial equivalence is a very important technique, and typically this is detected and enforced via conflicting operations. And there's two ways or two approaches in which you can do concurrency control so that serial equivalence is still maintained. The first is pessimistic concurrency control, such as locking, which limits concurrency but is always correct. Optimistic concurrency control lets transactions proceed with their reads and writes under certain conditions, but checks later on or enforces checks at some point of time so that the asset properties and serial equivalence are in fact always obeyed.